All right. Sorry for the long delay. 10 minutes. Uh, a lot of this you guys already know, so I don't think there's a whole lot of reason to spend a whole lot of time on them. There's adders, decoders. Wouldn't you know, they have to cut grass now. Adders, decoders, encoders. This is the one we're really, multiplexers is the one we're really interested in. Uh, Adders, decoders, comparators are something we're more interested in if we're working with microprocessor or microcontroller circuits, or if we're building microcontrollers. But let's see what we got. Um, we got adders. We're used to working in decimal, but they got binary or octal or hexadecimal systems. Here, you should know all this, how to convert from one to the other, right? I should just be able to say, uh, the tough part is knowing which system is it that I'm working in. Because if I say 10, uh, you may not know if I'm in decimal, octal, hex, or binary. So you may have to ask me which system am I talking about in some of these number things. But you should know how to move from one system to another. For a general adder, we basically have the two add-ins and then the sum bit and a carry out. And we just did, in the last one, we did a 4-bit adder using what? The components in there. So anyhow, this is what we have. If we were going to do adders in this class, we would actually do them uh, with VHDL. And one of the nice things I know that I like about it is with VHDL, if you add the right math library, you don't have to worry about it being binary, hex, or decimal. You just tell it to add them up and it'll do it. Here's a full adder, the truth table for that. Again, remember I told you the other day that this top one, when we're looking at those maps, that this one that said what is it? The exclusive ORs, that's what this K-map is. This is the carry. Okay, so here's those exclusive ORs, and here's those carry bits. Now, again, there's no real reason to go into these real deep. What I'd rather get into today is some of the flip-flops, because that we're going to be using a lot for the rest of the semester. Now here's Xilinx symbol for a 16-bit adder. Notice it's got 16-bit input on A, 16-bit input on B. That's the symbol that Xilinx uses for a bus. It's got a 16-bit sum. It's got a carry in, a carry out, and then this is, it says overflow, but what that's supposed to be is the V bit if we're working with a microcontroller, right? If there was a 2-bit or a 2's complement overflow. Okay, this one is a little different in that we've got an add and subtract controller here. If we have on one state, it's adding. If we got a different state, it's subtracting. Okay, here's a VHDL code for a 16-bit adder. Here we're using standard logic. Now this is real interesting, and you got to be really, 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 really careful with this. So if you're working with some other stuff back there, pay attention to this part especially. 15 down to 0. Why didn't I just say 0 to 15? Well, in Xilinx, it's the way that you're going to use the bits. Now I've got to, I hate this, but I can't go to the board, but I can call up Microsoft Word. So I want to ask you something about this number I'm about to type in. Let's get some big numbers up here. 20s. Okay, is that number in decimal? That's a binary number, okay? Is that number 10 or is that number 5? How do you know? Because what? This is the most significant bit? Is this the most significant bit?
If it's positive logic, it's 10. If it's negative logic, it's 5, right?
That's close. That's a good. But that's not it. So it could be either one, couldn't it? I should tell you? No. I want you guys to. This is what we're used to, right? And so we would say it's 10 because that is what we're used to doing. The most significant bit is to the left. We're used to doing that in decimal. We're used to doing that in octal. We're used to doing that in binary, right? We're used to doing it in all of them. It could be 5 in VHDL, though. If you're reading from this as the most significant bit over. So when you describe, as they've said right here, X and Y are standard logic vectors, that means it's a bus and it's got more than one bit. I don't know why they didn't call it a standard logic bus, but they call it a standard logic vector. 15 down to 0 is saying that we've got, for this number, it would have been 3 down to 0, because it would have been saying the most significant bit first. If you say 0 to 3, then the number that we have here is 0 to bit 3. And it's the same 4 digits. This is a 5, though, but this is if we've called this 0 to 3, and this is if we call it, how is that worded? 15, or let's say this one would have been 3, sorry. This would have been 3. This one would have been 3 down to 0. Okay? This one 0 to 3. So in Xilinx, it's extremely important. How are you defining these? We're used to this. So I would suggest that you do all of yours as down to, so that you have the most significant bit all the way on the left. You do not have to. And if you don't have to, I've got an example in here somewhere where I've got them mixed up. In one place I've got 0, 2, and the other place I've got 15 down to. And it can show you what kind of a mess you can get in. Okay, so this is just a 16-bit adder. I'm doing everything carefully. Everything's 15 down to 0, meaning that bit 15 is the most significant. It's all the way to the left. Bit 0 is the least significant, all the way to the right. X and Y are input buses. S is the output bus. Are you waving to me, or are you going to have a question? Okay. The 3, I just didn't want to do a 15-bit number. I just wanted to do a 4-bit number. So it's bit 320 would have been the 4 bits. Ah, okay. See, it's bad after lunch because everybody's sleepy and we're not thinking, all right, anymore. Right? Okay, you want to see that again? I was saying 3 down 2 because this is bit 3, bit 2, bit 1, bit 0. This is bit 0, bit 1, I'm sorry, bit 0, bit 1, bit 2, bit 3. That's where the 3 came from. Okay, again, the entity just tells us the inputs and outputs. This case, the entity looks a little bit different because, as I showed you here, this is a symbol for a bus or a standard logic vector. Okay, and you let's see, this allows us to use all the arithmetic operators with standard logic vectors, so we do have to have that in there. But if, like I've told you before, if you use Xilinx and you put in your, if you're using the wizard and you put in what variables you have and you tell it you've got 15 down to 0 for X, then it's going to know this has got to be a bus, and it's going to know that it needs these libraries. So it'll pull them in automatically for you. Okay. This one doesn't have carry in or carry out. It just says that S, the sum, is assigned X plus Y. That's nice. That's easy. Here's with the carry out and the sum and overflow and several other little pieces right here. It's also got a signal in there, which is a vector. This is a whole bus, and I've got 16 down to 0 instead of 15 down to 0. We're going to have to check that in a second. And it's a signal, so that means it's all inside the entity. It's a bus that we can't get to and we can't touch. So it says there's this signal sum, and it's 16 down to 0. So sum is the one that's got 17 bits. And here we've got sum is assigned 0 and X. This 0 is that 17th bit. It's bit 16. And here, this is some strange syntax for saying it's actually saying that AND symbol is saying concatenate these two strings into one. And 0, because of its placement, is the most significant bit. Okay, so that 0 comes first, and then X, which is a 15 or a 16-bit vector, comes right after that.
So is the 0 going to be the carry? Is that what that's pretty much going to
The
be?
0 is going to end up being the, what I'm doing is I don't want to have all these other bits floating around. I want to kind of deal with them all in one place. So that's going to be the carry out. So we've got that X with the extra 0 plus Y, which is a 16-bit number, plus a carry in. And we're going to get a carry, if we have a carry out, that bit 0, this bit is going to change to a 1 if we have a carry out. So here we've got S, the sum, is equal to this. Now see, sum here is a signal, so it doesn't even get to the output. So here we're defining it, here we're assigning it to that output, and it's a 15 down to 0. Okay, it's assigned the same value as sum. Okay, but we had a 16-bit number, right? Or I'm sorry, a 17-bit number. So the 15 down to 0 gets assigned to S for the sum. Sum bit 16 is assigned to carry out. Kind of weird? Kind of different? Does that make sense? Yeah. It'll make more sense tomorrow and the next day and the day after that as you get to use these for certain things. And then it's got the overflow. And to figure out the overflow, I'd actually have to go look that up. That's the sum 16 exclusive OR with X15 and several things to see if we've got a bit there that for overflow it's supposed to be 2's complement. So do we have a 1 when the number that would say it's negative, but the number is really positive? Or do we have a 0 saying that it's positive, but the result's supposed to be negative? And this is supposed to tell us that. Okay, so there's a 16-bit adder. Here's now all the stuff, like the AND is a symbol that means to concatenate. The preceding 0 is bit 16. Okay, so here I'm telling you a little bit more about it so you guys can go look that up if you need to. Here's the symbol that the code generates. It shows it shows if X 16-bit number in, Y a 16-bit number in, overflow and carry out are just bits. Here's the result, the sum, and here's our add and carry in. So that's what we get. I have no idea why I'm running out of breath, but I did take some of my meds right before I came down, so maybe that's it. It's messing with me. It happens. Here we have something interesting, some signed numbers. Again, signal here is a signed number, 16. It's the same thing, except we're dealing with signed numbers. So I wouldn't worry about it all that much. Everything that's in blue is different from back here. Here it said signed there. Here it says arith, and it says signed all through here. Okay, standard logic, because we have signed up here. Here we're saying arith for arithmetic up there, so we have to say signed all through there. This is the one I use most of all, because all I have to do is add this one line that says we're using standard logic signed numbers. Okay. This is interesting. Here's an easier way to do it. We're letting these numbers be in decimal. We're calling straight out. We're just telling us that they're integers. If they have a range from negative 32,000 something to positive 32,000 something, and an output with a range of basically the same thing. How big a number is that? How many bits is that? I'm sorry? 16. Bit 15 to 0. Here we say S is equal to X plus Y. We get the whole answer. Okay? And it just makes it a little bit easier. We do have to say arithmetic up here. But we do have to say the right range. Now, I've gotten into a little bit of trouble here because the range, I think I had the range where it was just a small number. I only needed like 8 bits or something, or a number value of 8. So I said it was 8, and then my result turned out to be bigger. And I got all kinds of weird errors there. So just make sure when you're doing something like this that you have a big enough range of numbers. But if you get too big, you're taking up too much space that you don't need to. And so you need to watch that. Multiplexers. So we just switched topics here. This one's the one that I think is more important than anything else in this whole set of slides, the multiplexers. Here's a 2-input multiplexer. Okay. With a 2-input multiplexer, here's our two inputs, W0 and W1. That's our data input. It takes 1 bit to decide between 2 bits, right? Or 2 values. So we have one selector, and that one selector, when it's 0, is going to take W0 and connect it down to the output, F. And when the selector bit is 1, it's going to take W1 and connect it to the output bit. Just like this is showing. Does everybody remember that about multiplexers?
I don't remember anything about multiplexers.
I'm sorry?
I don't remember anything about multiplexers.
Anybody else in that same boat?
Everybody put your hand up, don't lie.
Huh?
Everybody put your hand up.
Everybody?
Yeah.
Really? Yeah, Isaac, you know all about them though, right? Isaac knows all about them. I'm feeling bad, so maybe I'll let him explain it and I'll go on home.
Do it. I ain't feeling much better.
Okay. Gee, I don't want to have to go to the board for this, so I might end up having to, well, no, Word has got that symbol. Okay, let's go a little bit further and see what it does. Here's a simple circuit for that. That should make sense. We've got our selector bit, and if it's 0, then we'll have a 1 here, and let's say that there's a 1 on W0. Then we have a 1 here, and our output F is the 1 that's W0. This one's turned off because if this is 0, the input 0 to this AND gate makes this output 0. Now, if this is a 1, that inverter turns this gate low. I say turns it off. So W0 is not coming through, but whatever is W1 is coming through because this bit's a 1. So if W1's a 1, so is F. If W1's a 0, so is F. But it's whatever W1 is gets to the output when S is a 1. It's whatever W0 is when S is a 0. Right? Because that makes this a 1 here. So now if this is 1, the 1 gets to the output. If this is a 0, the 0 gets to the output. So this truth table is the multiplexer. They're also called data selectors. They decide which line you're going to choose for the output. Let's see what else we got. Okay, now we're getting to have some fun. Here's a 4-bit multiplexer, or you might hear it called a 4-to-1. But we've got 4 input bits. Now, to have 4 input bits, we need 2 bits to select which one do we want, right? If we had 8 input bits, how many selector bits would we need? 3. If we had 16, how many would we need? 4. You're getting it now. So if we have 5, how many would we need? 32? Yeah, that's what you said. Just, I couldn't hear you right, but that's what you said.
I'm looking at a way like 2 to the power of whatever it is what you use.
Exactly. And every time you step up 1 in inputs, you double the number of selector. Oh, I'm sorry, the opposite of that. Every time you double the number of selector, every time you double the number of inputs, you increase the number of selector bits by 1. That's what it was. Okay. So here, forget this circuit. And I hope the DE students can see that little cursor moving around. But forget the circuit. It's the symbol and the truth table. That's what we care about. Okay, that's all we care about. So now, let's say over here we had 0, 0, 0, 1. Look at that again. We have 0, 0, 0, 1. What kind of a gate is that? It's an AND gate. So that means I could hook up a 0 to this or ground it, a 0 to this or ground it, a 0 to this or ground it, and a 1 here, tie it high, and these would be like the two inputs to an AND gate. Because when I said 0 here, this 0 on this input goes to the output. When I've got a 1 here, this 0 on 1 goes to the output. When I've got a 2 here, that 0 on 2 goes to the output. When I have a 3 here, the high voltage goes to the output when that's a 3. So we can make this a truth table for just about anything we want. It would if it was an OR gate. What would W0, 1, 2, and 3 have to be? 0, 1, 1, 1. And then those selector bits would choose which one of those bits appears at the output. So if we had 0 for this and a 1, 1, 1, we have an OR gate. What if we had for W0, 0, this we had a 1, this we had a 1, and this we had a 0? What would you call that? A what? You said 0, 1, 1, 0. 0, 1, 1, 0. Exclusive OR. So it looks like we can create just about any kind of chip you want to create. Now, remember back to your homework. You guys were wondering, why did I give you that table that had A, B, C, D that counted from 0 to 15 and X, Y, Z, W, X, Y, Z that had all kinds of numbers in there? What was I doing? Any idea? A, B, C, D was supposed to be the selector bits to a 16-bit input or 16-bit multiplexer. The W, X, Y, or Z were the output for the multiplexer. And those inputs were in the table. Okay? So then we could spell that out on this multiplexer as a summation expression. We could spell it out as a VHDL expression or minimum SOP expression or anything like that. Okay, here is the exclusive OR gate, right? I got this out of a book. Why they changed all of a sudden to the selector bits being W1 and 2 instead of S and 0, S0 and S1, I don't know. But that's what that should be, because that's what it was right here. Right here. But they changed it to this. So we got 0, 1, 1, 0. We already said this was an exclusive OR. So if our inputs here were 0, we get a 0 on the output. If our bits here are 0 and 1, we get a 1 on the output. A 1, 0, we get a 1 on the output. A 1, 1, we get a 0 on the output. So this is an exclusive OR. And this is the way that Xilinx handles all of its logic. All lookup tables are really multiplexers. That's why they're so important for this class. And then for when we start getting into state machine design, we need also to know the way the flip-flops are working, because we could use different kinds of flip-flops for that. Look at this one. This one's kind of interesting. We're using one 2-bit multiplexer to create a 4-bit multiplexer. Now, these kinds of things I do ask you to do on the test. You've seen that on the practice test, haven't you? Nobody's looked at the practice test yet. So you're going to wait till the night before, right? That is not a good time. I've already told you that. That is the worst possible time to be looking at that. Anyway, okay, I do ask you to do something like this on that test. Take this truth table, and all you've got is a 2-bit multiplexer. Make it work. Well, you might have some other gates too, and by that, depending on how I word it, I do take a lot for granted when I word one of these problems. I assume you know all the other stuff I've got hidden in my head, and that you don't know, and you don't want to know. It's kind of a scary place. But you say here, and this is the same truth table as that one. When we have zeros on W1, we're selecting this one. When we have ones on W1, we're selecting this one, right? That's pretty simple. W2, it looks like since it's 0, 1, and I'm selecting this when I put a 0 on W1, it looks like whatever 0, 2 is going to directly to the output. If W2 is a 0, it goes out. If W2 is a 1, it goes to the output. For this one, this is what we want. But this is what we have for W2. It's inverted. So we tie an inverter there. Okay. What if it was 1, 1 that we needed there? What if this was an OR gate, not an exclusive OR gate? All we'd have to do, we wouldn't have to tie this to anything except for a high up to the supply voltage. Okay, and we would still have a 2-input multiplexer that would be working as a 4-input multiplexer. Okay, you ready to have more fun? Here's an 8-bit. They really play weird stuff next door, don't they? And I am so glad I can't hear it. Now, last night was bad. I couldn't hear something. And my wife tells me that when I whisper, it's about as loud as I'm talking now. And my in-laws were in the living room. My wife and I were in the kitchen. And I'm talking about them. And it wasn't nice. They tell you not to say nice or bad things about people, and I know better than to do that. But here I am whispering bad things about them, and she's hitting me in the side. I'm like, what? I'm whispering. She said, your whispering's like yelling. Shut up. So, of course, I couldn't hear her, but I could see the expression on her face, and I could read the lips, shut up, So, and now we still don't know if my mother-in-law heard that or not. We're waiting for her to lower the boom on me. So if I don't show up later this week, we know what happened. She found out, right? Bam! She'll take this stick from me and she'll just slam me upside the head with it. Wouldn't be the first time. Okay. And it all came over because, again, it came up because I couldn't hear. My wife came in and told me my mom and dad are coming over. I thought she said my mom and dad are wanting to come over. So I think, oh, okay, they'll call us before they come. She's telling me they've already called. They're on their way. I didn't know that. And I've got my grandchild in my arms, and I had just gotten her to sleep. And here comes the old bag. Mouth just going like that. I could have killed her. So that's what I was telling my wife. Why couldn't they at least call before they come in? Okay. So I'm in trouble. Okay, that was a nice little break. Let's get back to work. Here's just some random set of inputs and outputs. Or not inputs, but outputs. And it's not really random. It's like we could have had these inputs, and because of the logic circuit we were trying to implement, when we had 3 zeros at the input, we had a 0 on the output. When we had 0, 0, 1, we had 0. So this was the function, and we could actually come up with what this function was. Think of these as A, B, and C instead. And you've got, when we have a 1 here, we've got A naught, B, and C. When we have a 1 here, we've got A, B naught, and C. For a 1 here, we've got A, B, and not C. And for this one, we have A, B, C. Now we could put that in a K-map and come up with the minimum SOP expression. We could come up with that as a summation, which would actually tell us how to hook it up as a multiplexer, right? Because the summation expression tells you what value to put on bit 0, 1, 2, 3, 4, 5, 6, 7. Just like it tells you in the cells of a K-map, this cell has 0, this pin has 0, this cell has 1, this bit has 1. They match perfectly. That's why I've had you doing that kind of stuff, writing summation expressions, so that you could easily go to this. So we could create a K-map, and it tells us exactly what we're supposed to do for the multiplexer, which tells us exactly what the lookup tables should look like in Xilinx. And it is so much easier to develop circuits with a multiplexer than it is to do it with all the other gates. For example, I don't even know what gates this is. I don't know what the equation is here yet. I know what the summation expression is. It's 3, 5, 6, 7. That wasn't too hard. I could put that in a K-map. That wouldn't be too hard. But then to come up with well, I mean, we could put it in the K-map real quick. I use, I don't know what y'all use for that, but I use Excel. Because it's just too easy. So here's Excel, and I take these. Let's see, we had 3, A, B, and C, so we only need those. And for format, for the row height, it always says 15. I'm going to say 40. And then I do this, and then I say that all my text in there is about 18, let's say. So here's my K-map. I said we had in cell 3. So here's 0, 1, 2, 3 has a 1. Did somebody's phone go off, or did I just, something freaked me out? Okay, I didn't know if that was all in my head. It did. I had just moved my head like this, and I went, whoa, that was a weird effect. I told you I did some medication before I came down here. You guys are messing me up. Okay, so for a 3, 0, 1, 2, 3, this has got a 1. For a 5, so 0, 1, 2, 3, 4, 5, that's a 1. And then 6 and 7. So, well, we don't have a lot of luck with this one. We've got A and B, right? So this is A and B, and now we got these two and these two. So these two are B and C, right? And then the last two, these are A and C. So there is my VHDL, or my sum of products, the minimum sum of products expression for this table. Okay. So we get all that from, here's summation, here's the VH or the SOP, here's the truth table, and here's the multiplexer. So they all fit right together. Okay, and then we have to have something like this. What if we had a 4-bit multiplexer? We've got an 8-bit here, but we needed a 4-bit. Now look how this is done. We took W1, this one's really W1 and W2. Look at these two. They're both zeros. They're all 4 zeros. So that means no matter what, these two are choosing this. I said our output was 0. So it just doesn't matter what W3 is, our output was 0. Here, on these two inputs, we got 0, 1, and our output 0, 1. So we can put either a 1 there. No, we can't. We got to put W3, because that's a 0 and a 1, and that's what we want at the output, a 0 and a 1. Here we have 2 at this point. Those are 2. And we still want 0, 1, so that's still W3. And then here we have 3, and W3 doesn't matter anymore. We've got 1, 1 at the input, so we just put a 1 there. So what we've done is we've looked at, now we could choose any two of these, but you got to be really careful, because you got to choose 0, 0, 0, 0, right? And then you got to choose 0, 1, and 0, 1, and then 1, 0, and 1, 0, 1, 1, and 1, 1. So we could do it that way. There are several ways we could have 0 and 0, but it was easiest to just look at these and say these 4 are zeros, so I will use 1 and 2 as my selector inputs, and then I can see what I would get on the output if I connected W3 there. And I can also see exactly what I need from my output and just connect that there. Let's take it a step further. We could also use 2-to-1 multiplexers, and this we're now using W2 and W1. Here's W2 0011, and here's W3 0. So this is giving us an exclusive OR, and this one's giving us an exclusive NOR, and this is how we would have to hook it up. How would I do it? We're going to write it up in Xilinx, so it doesn't matter. It's going to decide if it needs 4, 8, or 2-bit multiplexers. We don't have to worry about that. But it is a fun little exercise, and of course I give it to you on a test. Now here's how to do multiplexers in VHDL code, because you are going to have to use VHDL code to do this. We're using S as our select bit, okay? So this is a new construct that we have in VHDL that we haven't looked at before. And we're saying with S, select this. So we're saying assign F W0 when 0. What does that mean? Well, that means when S is equal to 0, assign F a W0. W1 when others. What do you think it means by others? What are the only possibilities? When S is 1, right? Actually, these values, when we got standard logic, they can take up to 9 different values. High and low, 1 and 0, those as being different. 1 being 5 volts, 0 being ground, high being 3.2 volts, 0 or low being 0.4. And then there's several others, and right now I'm not recalling what they are, but I think there's 9 total that these variables could take on. So we could say W1 when 1, but it would have to have a single quote around it. Okay, that's to say it's this particular value. But what if it wasn't 1, it was one of the other values, like a high or something like that? Then we better say others, or we're going to get an error here. Okay, here's another one. It's just another way to write it. It does the same thing. Here we're using the with and select construct. Here we're saying when and else. So it's assign F W0 when S is equal to, notice a single quote, else assign it W1. So there's another way. There's 2 ways to do a 2-bit multiplexer. Here's a 4-bit. Here it gets real different. These are all input bits. S is an input standard logic vector 1 down to 0. So is this most significant or least significant? Most. So when we have, we assign F a W0 when we got zeros on the input, 1 when we have 0, 1. And notice now they're double quotes. When we have a single quote, that's for a single bit. When we have more than 1 bit, we have to use double quotes. Store it and don't forget it. All right? Some of your brains don't work any better than mine.
Probably worse.
So it's, no, probably not. So it's probably, you just got to be careful. I've made plenty of mistakes on these before I found out what I was doing. Okay, here's, we're putting a 4 to 1. We're saying it's a package. Here's a component. So we made a component or a subcircuit out of this, okay? And now we can map it like this, and we can end up getting a 16-bit multiplexer using 4-to-1 components. And again, this is one of those stupid little, isn't this a nice academic exercise here? But I would not do it. In the real world, I wouldn't do it. In fact, when we get to it, we're going to get to the point where we develop expressions, or we're actually not even going to do it as expressions. We're just going to say, well, I want our circuit to work like this. It does this, it does this, it does this. And then let Xilinx figure it out. So I doubt we will ever do something like this. But it's very similar to what we've had before. We've got our port mat. We've got our signal. We know that this is W0, 1, 2, and 3 by virtue of its space, its placement in this line, and W4, 5, 6, and 7 by their placement in this line, and so on and so forth. And that's what you get as the output. This is trying to show you got W0, W1, W2, and W3. And then here's W4. It's this line, 4, 5, 6, and 7. And this one's 8, 9, 10, 11, so on. S0 up here and S1, S2 and 3 down there. Okay, decoders. How many of you have used decoders before? Most of you not. Decoders I mostly have used in microcontroller circuits when I'm trying to add memory or something like that, and I want to decode blocks of memory, and that's usually where they're used. The way they work is all you have to do is look at the truth table. That's how it works. And you might be going, what? That didn't, what? Well, let's explain it. We got an enable signal. That's what that stands for. When enable's high, and it could be a not enable, meaning when enable's low, it would have a bubble here if that were true, a bubble at the beginning. And that would say when it's low, this thing is turned on. If enable's 1, it's turned off. Well, this one, no bubble, no line over it, no not before it. So it says enable, this chip is turned on when the enable bit is 1. Otherwise, it's turned off. And that's why it's saying here, when it's turned off, it doesn't matter what the two inputs are here. The outputs are always going to be 0 when this thing is disabled. When it's enabled, when we have 0, we're selecting this line, and this line goes high. The others we're not selecting, they stay 0. When we have a 1, this line goes high. The others stay 0. So we're only turning one of these on or one of these high at a time by these two inputs. Have you ever done that before or ever needed to do that before? It's a little different. But for memory and selecting memory, that works out real well. And I can show you examples of why that's necessary. Okay. That's the decoder. Here's one of the most typical, most used decoders that are out there. It is a 74138. It is a 3 to 8 active low output, low enable decoder, most often used in decoding memory. I've used these so often. And I'll bet if you go up in the lab and look, we'll have 74 138s up there because they're that common. It's like the, what's the most common op amp? 741? Is that what you said, or am I just dreaming that? I'm dreaming that. 741 is like one of the most common op amps that are out there. So here it works exactly the same way, except we got this bubble on enable. So this really should have a line over it. But it's telling us whenever the enable bit is low, this circuit is active. When it's a 1, it's inactive, and so the inputs can be anything. And because we have bubbles on the output, this is where it's active high or active low based on the bubbles. Because there's bubbles here, that means it's active low. Well, if we've got everything turned off, then all of those outputs are high. Notice this diagonal line of zeros. Okay? That's saying when it's on, when it's active, and I select line 0, that's the line that's going to go low. When I select line 1, that's the line that's going to go low. When I select line 2, that's the line that's going to go low, and so on and so forth, all the way down to here where we say when we select line 7, that's the line that's going to go low. Okay? So this is real useful for having 8 banks of memory out there, let's say all with 2K. I'm looking at some old EEPROMs that were 2K by 8. We needed not 2K, we needed 16K of ROM. So we used these decoders, and we used 8 of those 2K EEPROMs or EEPROMs, and we would have our 3 address bits selecting which one of those chips we were going to turn on in 2K blocks. Okay, here's a 2 to 4 decoder, and we got to be extremely careful on this one. This is the one I told you earlier. We're going to have one in here where I've got something down to 0 and the other one 0 2. So I've got my logic going both ways here. We've got W, which is an input vector, 1 down to 0. So we've got this W here that's going to be 1 down to 0. Then I've got enable, and I concatenate them there, which I create a standard logic vector that's 2 down to 0. Okay, and here's where I actually concatenate them. So I got the enable first, that's a 1 bit, and this is 2 bits. So we got 3 bits altogether for E and W. Then I'm saying this is the most significant bit. So we're saying Y is going to be this when we get a 1 on the enable and zeros on W. We're going to get this when we have 1 on the enable and 1 on the W. 1 on the enable, 2 on W. 1 on the enable, 3 on W. And all the others, we're just going to make it 0. Now this is odd, because I'm saying when I've got 0, I want line 0 low. Why is this one a 1? I mean, I'm sorry, this is active high. When I've got the enabled and I've chosen 0, why is this one a 1? It's because I said here, Y is 0 to 3. I switched that logic around. And I did it on purpose so that you would see an example of why it's so important to keep them all down to or all to. And since we always see the most significant bit as the leftmost bit, it is probably a good rule of thumb for us to always use down 2. Okay? In this case, I didn't. And look at the kind of mess it could get you in. This really is bit 0. I'm telling it here when the enables 1 and W, the select, is choosing 0, make line 0 go high. Let the other ones be low. Here I'm saying when enables 1 and I'm selecting 1, let line 1 go high. All the others have got to go low. When enables 1 and I select line 2, let line 2 go low. But that looks weird because it's backwards from the other ones. Okay? And then we've got, if I had made Y 3 down to 0 instead of 0 to 3, we would have had it like this, and all of a sudden that seems to make a little bit more sense, right? Because then this is bit 0, this is bit 1, bit 2, bit 3. Okay, here's a demultiplexer, which is basically functions the same as a decoder. So I'm going to just let it go. Here's our input, and these outputs, it's going to act like a decoder. And so we can look at all the other ones if we want to. Here's an encoder, works the opposite of the decoder. Here we have some logic input here, and that's going to tell us basically which one of these, let's see which one. Okay, exactly. We've got an enable. Here's our encoder. We've got a logic circuit with 2 to the m inputs and n outputs. Exactly one input should be asserted. So only one of these should be asserted at a time. And then if this is asserted, and this is enabled, that's saying that only this one goes high. That's okay. My mind just went blank on that one. Sorry. When I've got 0 here, these are 0. When I have a 1, or when this one's asserted, I have a 0, 1 here. Okay? When I have this 2 asserted, this is 1, 0, or 2. And when I have a 3 asserted here, this one asserted, then this becomes 1, 1, or a 3. So what we've done is we've taken this where 1 bit represents a number, and here we're turning it into a 2-bit number, and so we're reducing the number of bits it takes to actually encode that. Here's a diagram of the way the encoder works and a truth table. I do want to, we're about out of time. Here's the VHDL for it. We're probably not going to use a priority encoder, but if you're going to use it, you're going to go look it up. Okay? And then we got comparators, and I do not want to go through all this stuff for a comparator. All you have to do is the VHDL code that says if A is equal to B, make that a 1 when A is equal to B. Else make it 0. That's pretty simple. Okay, that's it for today. I will see you all on the next time, whichever time that is. And if I had showed up on time, I wouldn't have had to rush through those last few slides. Right? Okay, let me okay, all I gotta do is stop this.